Hello everyone, my name is Guanghui. Today I'm going to present our work, the NLP task effectiveness of long-range transformers. It is well known that transformers have dominated the state-of-art of natural language processing, but they are also suffering from their quadratic time and space complexity. To make transformers able to handle long sequences, people propose a variety of long-range transformers. They can reduce the complexity to sublinear or even linear. They are guaranteed to be very efficient, but it is yet to answer whether they are effective. Before we dive into the details of the paper, let's take an overview of long-range transformers. In the picture is a self-attention block of a standard transformer. All the tokens can attend to each other. The first type of variant is recurrence, where they chunk the text into different blocks, and each block can attend to past activations. A typical work is transformer XL. The next type is pattern-based methods, where they try to specify the attention matrix, for example, block-wise attention, or a sliding window. A special pattern is named global tokens, where certain tokens can set to be visible to all the other tokens. A typical work is a Longformer. The last type of method is kernel and low-rank methods. Instead of calculating the attention matrix, they try to approximate results with some mathematical tricks. For example, performer. These methods of course come with certain evaluations, but they are mostly non-NLP or simple NLP benchmarks. For example, long-range arena, which is comprised of synthetic datasets, language modeling, and protein sequences. Instead, we try to cover a broad range of NLP applications, including span level prediction, for example, coreference resolution and extractive question answering, sequence classification, for example, natural language inference, sequence to sequence generation, for example, abstractive QA, and summarization. We cover 5 different NLP tasks and 7 datasets, trying to provide a general guidance for the NLP practitioners concerned with long documents. We note our method is not a cross-model benchmark. It is unfair to have a side-by-side comparison between models because of their discrepancy of model sizes. And some models have different pretraining status or do not have a pretraining at all. Instead, we try to ablate long-range attention and trying to answer the question whether long-range attention really helps the performance. For example, for the recurrence method, we try to ablate the cross-block attention to restrict the receptive field of long-range attention. Some models do not provide any pre-trained checkpoints, for example, the kernel methods. So we try to migrate parameters from a pre-trained model to them, and trying to see if they can preserve the performance of the original model. We have some observations. Some of them are consistent with their papers. For example, we found that recurrence is generally useful and can boost the performance. We found that pattern methods can help the question answering problems, and seek-to-seek tasks can be benefited from long inputs. However, we also have some surprising findings. Kernel methods lead to dramatic performance drop, which makes them totally unusable. Specified patterns do not improve the span or sequence level tasks, and the recurrence can be limited by their attention range and can be much improved. Beyond those observations, we also want to answer 2 questions. How are they helpful, and why are they not working? The fundamental question to answer is that is it really necessary to have a long-range attention? We conduct experiment with a Longformer on coreference resolution and document-level natural language inference. We chunk the text into fixed lengths of segments and process them independently to restrict the long-range attention, whereas the infinite symbol indicate that we do not restrict attention at all. Surprisingly, we find that simple chunking is still a very strong baseline for the long-range transformers. And sometimes the Longformer with a short range attention can outperform the unrestricted baseline. It is likely that the long-range transformers are good at long documents but suffering from short ones. To exclude this possibility, we split the text according to the document lengths and rerun experiments on the fine-grained subsets. In the diagrams below, we find that the performance difference is consistent across different document lengths, and for the long documents, the performance margin is even larger. So that we again confirm that the distant information is not exploited by long-range transformers, and sometimes they can even hurt the performance. Then we turn our focus to the recurrence methods. We conduct experiments with XLNet on the coreference resolution and dog NLI. In the two diagrams below, the pink bar is the baseline where the long-range attention is restricted, and the blue bar is XLNet performance. We found that recurrence generally improves the performance, sometimes with a big margin. However, it is yet to answer how much does each segment contribute to the final prediction. To answer this question, we perform attribution tests on the documents. We leave the details in the paper and only show the results here. Please note that the prediction is made on the last token. We found that the contribution of the left part of the document or the distant segments is really low, which means that their signals are lost during forward propagation. Then we conclude that the recurrence is helping the performance, but they can be much improved if the issues can be fixed. Then we turn to the kernel methods. We said in the previous slide that we would migrate parameters from pre-trained models to kernels. Equivalently, here we replace the BERT self-attention blocks with kernels. We preserve all the parameters and perform certain fine-tunings for model adaptation. The tasks here are coreference resolution, dog NLI, and trivia QA, which is an extractive question answering task. In the diagram below, the pink bar is the original BERT model performance, and the blue bar represents the kernel performance. Surprisingly, we find there is a dramatic performance drop if we replace BERT with kernels, which means that the kernel in this scenario is totally useless. We speculate kernel methods can generate certain approximation errors, and BERT is comprised of 12 stacked self-attention layers. Each layer will take the output of the last layer as input, so that the errors can be accumulated. To verify our conjecture, we try to do a layer-by-layer replacement. We do not do any fine-tunings here. From the diagram, we can see that as we replace more and more layers, the performance of the model would drop accordingly. Note that the kernel methods would use random features to approximate the matrix multiplication. So to exclude the possibility of insufficient random features, we try to increase this number. But until the random features are so many that the computational workload is not reduced at all, the problem still cannot be fixed. So that we conclude that for deep transformers, kernels lead to dramatic error accumulation and is practically non-usable. Long-range transformers also have some good sides. In this study, we try to understand why global tokens are helpful. Please note that global tokens are tokens that can attend or be attended by all the other tokens. We conduct experiments with the Longformer on question answering, where queries are naturally set as global tokens. We first try to ablate long-range attention, and we found that long-range attention did not make a big difference. But if we plug in the global tokens, the performance of the long-range transformer can be significantly boosted. So our conclusion is that instead of long-range attention, the global tokens are truly the key to the success. Then a natural question is, how do global tokens help? To answer this question, we do attribution tests on queries with and without global tokens. We found that queries with global tokens have a much higher contribution to the final prediction and can attract much more attention, which might explain their superiority on the question answering tasks. Our last topic is content selection in seq-to-seq models. To investigate the effect of long-range transformers on seq-to-seq models, we conduct experiments with LED on some FD and Gov report to summarization tasks. LED stands for Longformer encoder decoder. To ablate the long-range attention, we try to chunk the source sequences into fixed lengths of segments. The infinite symbol indicates that long-range attention is not restricted at all. In the below two diagrams, we can see it is consistent that the performance of LED increases as the segment length is longer, which means that a long-range transformer, long context bring better performance. Moreover, we want to investigate the advantage of long-range attention on summarization. We try to measure the entropy of the cross attention with and without long-range attention. In the diagram below, the blue bar is the entropy with long-range attention, and the orange bar is without long-range attention. We can see that long-range attention brings consistently lower entropy, which can be translated into higher selectivity on the source side attention. It is reasonable because we believe that a good summarizer should skim over the whole document but focus on certain areas, and the long-range attention enables the summarizer to do so. As a conclusion, we have some takeaways. Based on our experiments, we believe that long-range transformers have advantage when explicit query exists, or for sequence-to-sequence generation tasks, or if the recurrence is used. They could have no effect for the token or span level predictions, or for the sequence level classifications. We strongly advise the practitioners not to use kernels if you have deep transformers, or the accumulated errors can ruin the performance. Thank you for listening. We understand that it's really hard to understand so many figures in a short period. Please reach out to our papers to find more details. Thank you again.